How are you all doing? Great, great. Before we get things started, let me do a quick poll. How many of you are fine-tuning the foundation model or large language model to implement your generative AI implementations? Awesome, awesome. There are a few raised hands. Cool. So today in this session, you will learn from S&P Global on how they fine-tuned the foundation model using Amazon SageMaker, deployed that in Amazon EKS, operated at scale, and actually handling staggering number, which is 6 million inferences in a week, all while optimizing the cost efficiently. My name is Prashant Punath, Solution Architect at AWS. I'll be joined by my customer from S&P Global, Dushyant Shekhar, and Saeed later today to talk about their journey. So before diving deep into the business problem that they had in the financial services industry and how they decided to use this fine-tuned foundation model as the design pattern to solve that problem, and how they created the distributed architecture in AWS, and the lessons learned from that, let me spend a few minutes to level set you on what we are seeing across the customer base when they build the generative AI solutions. Customer build their Gen AI solutions on top of their key differentiator, their data foundation. Data foundation built on AWS that provides scalable, secure, resilient, price-performant storage options with various data integration solutions that quickly help customers to build the Gen AI applications at scale. Once customer decide, okay, for this particular business problem, we need Gen AI to really solve that, the practical use case, scale it at enterprise grade, they embark on a journey on a pattern selection. Some start with prompt engineering, or retrieval augmented generation, or fine-tuning, or continued pre-training. As you might have observed from your experience, and the chart shows, the quality of the model increases as you go from left to right. And it will be more domain-specific, domain context as well. It gets smarter in that dimension. But the trade-off is the complexity, the time, and the cost to make that happen. In S&P, in order to solve their complex business problem, they chose the fine-tuned foundation model as the design pattern. Let's hear from their journey. Let me introduce Dushyant to the stage.
Thank you, Prashant, for teeing this up. So I'll kind of give you a little context on the business use case here, and then my colleague Saeed would kind of take you under the hood and give you little details on what we did. So as Prashant mentioned that, for S&P, data is the business, right? So everything we do revolves around data. And even before the term probably big data was coined, we were dealing with big data. We just didn't call it that. So data is foundational to everything we do. So we give you a little, I think most of us are familiar with credit ratings. So a little bit of a context here that kind of distinguish our ratings business from this use case. So a credit rating, in layman terms, is kind of the probability that the obligor will meet its financial commitments, right? It's very plainly put. So the obligor could be an institution, a government, and the S&P credit rating business is over 150 years old. We have about 1 million outstanding credit ratings in the market, on which about $46 trillion of debt is riding. So that's a standalone division. Those ratings are predominantly based on financial analysis. But then there is this whole private market space, which we represent market intelligence. And that's a big area of commercial opportunity for us. So, and giving credit ratings for private companies is a tricky business because a lot of these private companies in a lot of jurisdictions are not obligated to file financials. So we have to look at other signals to be able to kind of meet the needs of our customers who are kind of dealing with these private companies, right? So we call them SMBs, small and medium enterprises. They could be less than $1 million in revenue. But some of our customers could have like 100,000 of these as suppliers, counterparties, and things like that. So in absence of financial reports which are kind of regulatorily available, so we have to look at other signals to come up with what we called, this is an example of a risk kind of gauge report, which enables our customers to make quick decisions about doing business with these SMBs. So this problem has been there in the industry for years, and in absence of the latest technologies in terms of Gen AI or even just the availability of data itself, in the past made it difficult to kind of credit score these companies, right? So basically we don't have any financial information, so we're looking at more a signal-based kind of system. So here are some kind of challenges, right? Like we have to have like a out-of-the-box assessment. Our customers could have large portfolios of these SMBs who they want to assess very, very quickly. And as I said, even in the US, private companies are not obligated to file financials with any regulator. Right? In Europe, you could go into like things like Company House, or in the UK or local kind of agencies where you can get this. But these are not reasoned, right? So it's not like the earnings happens and there's a report available on the SEC. So sometimes these could be very, very old, right? By the time the event happens and the financial is all actually available, it could be like 3 or 4 months, which is not amenable to our customers because they want to do these credit assessments pretty much real time. Now you could look at other information in lieu of these absence of financial information. Is like you could look at, okay, are the management changes happening too frequently? What is the payment history? Are there any liens? Are there legal filings on this? And all these information then can be used as signals to come up with some quantitative way of coming up with a credit assessment. The timing is very, very important because the lag is not something which our customers accept, and the sooner we can give it, it's also a distinct competitive advantage for us. And as a credit manager, I myself come from S&P ratings that I would rather have more than less. All right, so I will have more quicker than having less information. So this is the kind of the challenge we face, and we're talking about north of 60, 70 million companies who kind of fall in this umbrella, right, which don't have financials, but they are doing businesses with a lot of our clients. So this is some ways to kind of overcome this problem. One is, of course, you could go look at the web and look at first-party information, like textual footprint of the companies. But this poses technology challenges that, let's say you have to keep a track of 50 million, 60 million websites. Like if you take plain vanilla web monitoring approaches, just setting up a spider on each website could be very labor intensive, right? Then there are like second-party information, which kind of more comes from journalistic articles and things like that. And in some cases, the first-party information could include financials, but we are talking about cases where we don't have that, right? And that's the best option because that has the highest veracity. So what comes from the company would supersede hierarchically any other information we get. And then there is always the option to go to social media and things like that and track third-party information. So that's broadly the space where we can get information. And then how do we get it and what do we do with it is something Saeed will kind of cover. But the strategy is broadly, you could consider these tasks as microservices. So given an example, one of the things we would want to do is to come with an industry classification for this private company. So if people who are from the financial industry, you're familiar with the standard GICS kind of classification, but this doesn't apply to most private companies because these GICS classifiers were never meant for kind of new age businesses. So we have to first establish a class of industry, right? Like, for example, blockchain is not a GICS classifier, so you could have many. And also now you find companies having multiple classifications, right? Like, what would you categorize Amazon as, right? So you could have multiple classes. So then quantitatively we can establish an industry kind of risk score once you establish the industry, which then enables us to, so this could be a task of classifying. Then there could be a task of tracking events, right? So every time there's a management change happens in a company, that could score in a certain way in our quantitative model. But all this information has to be passed real time. So the way you could look at it is, right, rather than building a big aircraft carrier, these are kind of smaller boats which kind of operate independently. And then there is also the architectural side of the complexity, which Prashant alluded to, that how do you make these work seamlessly, right? Because these pipelines run like daily, and they are completely human touch free, right? There's no credit analyst coming and looking at it. So the model does all the data collection, the classification, the parsing, puts it to the quantitative model, and the reports kind of are getting published. So the frequency of this is real time. I think it's all about, I mean, in theory, you could track the web every hour if you want. It's just about how much do you want to go there, because the costs get pretty prohibitive if you do it too often. And then there's the final risk report which comes out. It could be at a company level, or you could even run it for your own portfolio. So with that, I'll kind of pass it on to Saeed, who will kind of take you through the technical details of it. Thank you so much.
Thank you very much, Dushyant. Thank everyone for joining this session. My talk has three main sections. I'm going to introduce how we are scraping textual footprint of companies from web. Then I will walk you through how we are leveraging fine-tuned LLMs to extract relevant credit signals from those web pages. And then at the end, I will basically share some of the learnings that we had as we pushed these models to production. As Dushyant explained, in S&P Global, we are collecting data from many different sources, and our group is mostly focused on leveraging natural language processing for collecting data from documents and web. For the product that Dushyant introduced, there are few problems that we need to solve. First, given a URL from a private company, we need to map every child URL that is related to that company in a specific domain. This is what we call domain graph. Then within that domain graph, we need to identify child pages that they have basically relevancy for our use case. And then after we have those child pages identified, we need to look into section of the HTML file that has relevant risk signals and pinpoint to those sections. We also need to monitor those sections every week, right? And these are signals that we are capturing, and they end up in our credit models. And lastly, but not least, we need to do this at a scale. We need to be able to cover the target coverage of this product, which is 100 million private companies. So how are we doing that? So the first step for us is to creating that domain graph, which means starting from a URL that we have from a company. It can be the homepage of a company, or it can be any other page. We start by traversing up to 3 levels into that URL. You can think of this as a directed graph representation, where each node is a URL, and edges are connections between URLs or hyperlinks between URLs. So looking at that graph representation, can we just identify what are the priorities for us, right? Like which pages they need to get higher priority for our processing without doing any NLP? And the answer is we can use, for example, graph centrality methods, right? Like these are kind of telling us what are the pages that they have most connections, and that's where we start our processing. After that, we need to classify within those child pages which one is actually important for us. That classification part is the main topic of my second part of the presentation that will leverage LLM for it. So far we have that domain graph now, and we have identified those child pages that are important. Now we need to, within the HTML file, we need to identify section of the HTML that has relevant signal for our use case. These sections can be like sections that they talk about management of the company, and we also need to track those sections over time. We need to track like how much management of the company changes over time. You might be asking why extraction from HTML file is actually challenging. At the end, HTML is a markup language, right, that shows up very nicely in any web browser. The answer is when HTML was designed, it was designed to be very flexible and forgivable. So in an HTML, you can kind of define a table with just a span and div, or you can define a table with proper table tag and TR and TDs. And when it comes to private companies, there's tons of variations across how companies, they kind of set up their websites. All those makes extraction from HTML files challenging. Also, modern web is full of JavaScripts. There is a lot of basically loading that is happening dynamically in modern browsers. And because of all these, sometimes extraction from HTML is actually much more challenging than extraction from PDFs. As Dushyant kind of introduced, traditional approaches to extraction from HTML, they normally rely on rule-based methods. They anchor to XPath, which is a reference to an element in HTML, and they track changes in that XPath through time. The main problem with these traditional approaches, they have huge amount of false positives. So any geometric change in the page, it can trigger an alert, but that doesn't mean that the company has had any relevant signal for us. So how do we resolve that? And this has been an area of innovation within our team. So starting from an HTML file, we convert that HTML DOM to a tree structure. This is, to be exact, a heterogeneous graph. And for each node in that graph, we start growing feature space for it effectively. You can think of these feature spaces like series of, I don't know, div, h2, person name, or table, TRTD, product ID, or product descriptions, right? These are those kind of boxes that you see in this plot, right? And you can guess, this is effectively like an embedding, right? And you can guess where we are going with this. With that meta path in that graph, we can train an ML model that effectively classifies that meta path to classes that we are interested in. And that's how we are resolving that kind of issue with scaling up traditional web crawlers. So instead of anchoring to an XPath, we classify a meta path. Regarding our orchestration, so this is a pipeline that runs on a weekly frequency, and we are covering up to 100 million companies. We are leveraging Amazon managed service for Airflow. And in Airflow, effectively, we have a DAG, right, that has three main components: sitemapper, a scraper, and extractor. Airflow, it just instantiates our pipeline through API calls, right? And those API calls are tasks that we register them in queues that we leverage Redis to maintain our queues. We leverage Redis to maintain our queues, and we leverage it to kind of keep a status of our jobs as they get populated. And then we have worker nodes that are running in EKS pods. These worker nodes, they listen to the queue, and they start picking up jobs as they appear. You might be asking, like, we have seen during this week a lot of basically different talks around like leveraging SQS, and SQS is great, but for this use case, we leverage Redis, and it gives us a lot of benefit. Redis is an in-memory database. We can use it for management of our queue, and we can also store the status of our web crawlers as we traverse through that domain graph with a very low latency. And we don't need to hop between, let's say, SQS and a persistence that is happening in S3 and do a lot of IOs. We also did a lot of engineering to make sure that we can scale to the level that we need. At peak, we are running around 400 pods concurrently to just do the scraping. And they are small pods, each of them 4 CPUs running 64 parallel jobs. One of the things that we are doing is, for example, separating our heavy scrapers from light scrapers. And heavy scrapers are responsible for pages that they are heavy JS, right? Like they have a lot of JavaScript components. Sometimes we need to stay longer on them to kind of dynamically load the data. And for storage and monitoring, we use typical stack. Because of the sheer size of the process that we are running, we have seen a lot of value from using Amazon OpenSearch for our logging. So far, we talked about creating that sitemap of a company, and now we need to identify actually which page has signals related to credit risk. There are a few complex cases. They are complex classification and extraction cases in this use case. For example, identifying business activity of a private company is not an easy task. There is a lot of ambiguity normally when companies, they describe their main business. Or sometimes we notice that like the description between the homepage and child pages are not very consistent. And large language models, they are really powerful for language understanding and dealing with ambiguous text. And for that classification use case, they really shine compared to traditional NLP approaches that we have been using in our group in the past. Also, LLMs, especially when you fine-tune them for a particular domain, let's say for credit risk, they are actually great multitaskers. So it sounds counterintuitive, but for this product, right, like if we wanted to just use traditional NLP, then we had to train multiple different models for multiple different classification and extraction tasks. That model lifecycle management is actually something that it is not easy. LLMs being great multitaskers, you can have one model that does multiple different extraction or classification, that same model. And that decreases the complexity of lifecycle management for use cases like this. It's not the solution everywhere, but there are some benefits to it. But we have all heard that fine-tuning LLMs are costly, very difficult, and running them in production is very, very challenging. In the next section, I'm going to kind of walk you through what we did and how we resolved that. So first, let me kind of describe what is a fine-tuning. What is a fine-tuning of a large language model? So fine-tuning is a process of updating hidden representation of a pre-trained language model with the objective of making that pre-trained model better at a specific task. When we do full fine-tuning, it means we update all model parameters. And because we update all model parameters, those hidden representations, they get updated, obviously, as well. Because we have to update all model parameters, we need to have a lot of compute, multiple parallel GPUs that are running, and we need to have a lot of training data because we need to update a model that has 7 billion parameters. That's very expensive. Also, fine-tuning, full fine-tuning has one additional practical challenge, and that's when you do full fine-tuning and you have, let's say, 3 different downstream tasks, each fine-tuned model, they have the same size of your original pre-trained model. So in the case of Llama 2 7B, which we used, it is around 14 gigabyte of size. If I fine-tune it for 3 different tasks, 3 different fine-tuning, 3 different full fine-tuning, then we end up with 3 times 14 gigabyte models that we need to kind of maintain in production. Parameter-efficient fine-tuning is resolving that. And parameter-efficient fine-tuning, the idea is very simple. It says if the objective is to update hidden representation of that pre-trained model, for that objective, we don't need to update all model parameters. We can just get to the same updated hidden representation by training these small modules that are called adapters that they get injected into the architecture of the model. That decreases the complexity of fine-tuning significantly. Let's say, for example, for Llama 2 7B, parameter-efficient fine-tuning only requires around 5% of the parameters of the model to be updated. And 95% of them, they stay frozen. Another benefit is because we are doing we are updating only those modules in blue, those adapters. Now we have one base model that has 14 gigabyte, and we have a couple of maybe 3 sub-modules that each of them, they only size maybe tens of megabytes. This decreases the complexity for us. But still, doing parameter-efficient fine-tuning, you cannot do it on one GPU. You need to have a cluster. What we did, we used a method called LoRa, which is a low-rank adaptation of pre-trained models. And LoRa, that adapter is sitting in parallel to that feed-forward layer. And because it is using low-rank matrices, the number of parameters that needs to be updated are significantly lower than the parameter-efficient fine-tuning. So in the case of LoRa for Llama 2 7B, we only need to update 0.1% of the model parameters, which is 7 million, right? So now we are getting to the area that we could actually deal with those models 4 years back, those size of models 4 years back. But the benefit is all that knowledge base that is already available in that initial pre-trained model. So that significantly decreases the complexity for us, and that's what we did. There is a lot of good research around doing parameter-efficient fine-tuning and quantization together. Quantization is converting a model from, let's say, 16-bit to 4-bit without a lot of loss in the performance of the model. And when you do quantization, you are decreasing the size of the model to 4s. So in the case of Llama 2, 14 gigabyte becomes 3.5 gigabyte model. That makes things much easier. You can run it almost on the edge these days. Fine-tuning is only obviously successful if we have quality data but how can we build that quality training set? For this use case, we didn't have much annotation in S&P. This is a new domain for us. And we leverage the waterfall approach. And in the waterfall approach, the idea is simple cases, it goes to a rule-based pattern matching engine. And anything that kind of does not get classified using that rule-based falls into a self-grading pipeline that has larger LLMs at the top and a self-grader at the bottom. This is an agentic approach to creating training data. You effectively distill the knowledge of a large pre-trained 70 billion parameter and teach your smaller model to kind of understand that domain based on that training set. The self-grader is kind of just sends another prompt and asks your large model how comfortable it is, or like what's the level of confidence in that classification exercise that it does. And if the answer is very confident, that can go directly to the training database. If not, we send it to the human annotation pipeline. Two main kind of takeaways here is if you have limited resources and use cases like this, it's always a good idea to use a self-grading approach. And don't ask your LLM too many questions at the same time. Break it to pieces, and normally it works much better than having a very large prompt and asking to do too many things at the same time. For fine-tuning our model, we leveraged Amazon SageMaker. The starting point for us is obviously the configurations that we had for our quantization and the low-rank adaptation. Creating a quality instructions and answers is key to basically having a successful fine-tuning. There is another benefit of doing fine-tuning language models. This is very basically back to the strategy slide that Dushyant had. It gives you extra level of controls over the output shape of the LLMs. For example, in our prompt template, we limit the number of tokens that can come out of the LLM because we are just looking at doing classifications, right? We are not doing any generation tasks here. We are not expecting the LLM to return a couple of paragraphs of text. We also, with that limitation, right, like and limiting the number of tokens, we can significantly control the hallucination of these models. So you're training it really for your downstream task, and you have much more control over it compared to using just out-of-the-shelf pre-trained model. It's also a very good idea to stick to the initial prompt template of these models. So if you're using Llama, check what was the prompt template that was initially used, and don't change it too much, right? Like because the idea here is you just want to tweak your model a little bit to work better for your use case. You don't want it to forget everything that it has learned initially. On the SFT trainer part, this is just basically where the hyperparameter tuning of the model happens. Effectively, you want to get the best combination of training efficiency and your model performance. And we have a lot of internal models that are based on traditional NLP, and we are leveraging them as challenger models. Okay, so for the part that we are doing the classification and extraction, our architecture is identical to almost what we have seen before. So those worker pods that are in EKS, they listen to another queue in Redis. and they pick up these classifications and extraction jobs, and kind of they return the result. One thing that we did was we obviously fine-tuned our models in GPU, but we converted them at the runtime to CPU. And there is a very good open source library called Llama C++, and that's basically that library enables conversion of a pre-trained model from GPU to CPU. And it also supports quantization. So we converted our model to run it on the same CPU clusters that we had for our previous steps. Walking you through some of the lessons that we have learned. So it's always a very good idea to start simple. We heard the keynote earlier today, and that was the main message of the keynote as well. It's always good to start simple and then expand complexity. So start by picking up a small LLM, 7 billion, 8 billion parameters, leverage methods similar to LoRa, just fine-tune maybe well below 1% of the parameters of that model, see how it works in your use case, and then if it is really necessary, increase the complexity. There is additional benefit, I think I touched on this, when you do update only very small subset of parameters, you are much less prone to any overfitting risks, right? And also catastrophic forgetting. Catastrophic forgetting is when effectively, as part of the fine-tuning process, your model forgets the initial learning that it had because you're kind of too much surgical in that model. And normally, just basically doing a smaller scale fine-tuning, your model becomes much better at doing out-of-context performance, right? As your domain grows, your model is basically reacting better to it. And it has significantly lower cost. Effectively, all these fine-tuning, we could do it on a single GPU machine in SageMaker in around 16, 17 hours for one full end-to-end training. If you have use cases similar to what we are doing here, and you're using smaller models, and effectively you're thinking to transition from traditional NLP for basic classification and extraction use cases, which are 80% of what is needed in the industry, and you're not really requiring a lot of generation, right, from your LLMs. Consider and compare price performance of CPU and GPU. In our use case, it made a lot of sense to stay with CPU. Obviously, one single instance of GPU is much faster, but the price is 3 to 4 times of a single CPU instance that can run one inference, right? So it makes a lot of sense for cases when you have pre-processing or post-processing steps that they are running in CPU, just do the model inference in CPU as well, and do the math and see if that basically works better from cost perspective. So that's most of the things that I wanted to share with you, and with that, let's look at how all of these are tying together in the Risk Gauge report.
Introducing Risk Gauge Desktop, a focused experience designed for corporate credit risk workflows. Now you can view your entire portfolio on a single dashboard that showcases the details that matter most to your business. Check your aggregated risk gauge score to understand your overall risk exposure and how it's trending. Anticipate credit movements with early warning signals tied to critical market drivers. Tap into our Knowledge Hub for timely and relevant insights. Looking for a broader perspective? Understand how global economic and country risks could impact your entire portfolio. Then, stratify your exposures by country and industry to dig into the insights provided by the early warning system. You can also zoom in on individual companies to uncover critical details and key business drivers. Instantly generate a company credit assessment and peer comparison by leveraging our extensive private and public company database. Access comprehensive business credit reports for millions of companies and produce customized risk-gauge business credit reports that cut through the clutter to deliver actionable insights. Get a clear view of your customer credit risk. Explore Risk Gauge Desktop and transform how you assess, monitor, and manage customer credit risk. Now available on S&P Capital IQ.
Thank you very much.